Welcome back to Calculus 2. In this video we're going to talk about absolute convergence of a series. And to check that, we're actually going to look at the ratio and root tests. So let's start off with a definition of absolute convergence. A series converges absolutely if the corresponding series of absolute value terms, so the sum of the absolute value of a sub n, converges. As we'll see in the theorem on the next page, this is actually a stronger condition than just converges, because if terms can be both positive and negative, well, that means they might kind of cancel each other out to the point where they would converge. We'll see that in the next section when we talk about alternating series. This means they all have the same sign, so that means the terms are all small enough and decreasing fast enough that they converge. Decreasing towards zero fast enough that they converge. A lot of the series we've been dealing with were absolutely convergent because a lot of them were non-negative or positive. Geometric series are absolutely convergent. P-series that were convergent would be absolutely convergent. So here's the theorem I was talking about. If a series absolutely converges, then it must converge just regularly without the absolute value. So how does this work? Well, the proof of it is actually pretty simple. We know just from algebra that a sub n is less than or equal its positive absolute value and greater than or equal its negative absolute value. Because it's either a positive or a negative number. This is the highest it could be, this is the lowest it could be. So, a sub n plus absolute value of a sub n is less than or equal to 2a sub n. To absolute value of a sub n less than or equal 0. Just add the a sub n to all three sides. The absolute value of a sub n. How is that helpful? Well, one of the big tricks of this is that we're going to use our comparison tests to prove this. And comparison tests are only good for non-negative series. Well, 2a sub n is convergent to absolute value of a sub n is convergent since a sub n is convergent. In absolute value. Since a sub n plus the absolute value of a sub n is less than or equal to 2, well, I will say is non-negative, and less than or equal to 2 absolute value of a sub n, it must converge by the direct comparison test. How is that helpful? Well, now we know we can express a sub n as the sum of a sub n plus absolute value of a sub n minus the absolute value of a sub n which is the difference of two convergent series, so it must be convergent. So we set up most of this artifice so we could get a statement about something like a sub n being convergent, so we could express a sub n in terms of it. It's some of the massaging you have to do for simple proofs sometimes when you need to fit some property of convergent. Upshot, this thing, now that we've finished proving it, absolute convergence implies conditional, i.e. regular convergence of a series. That's absolute convergence. Let's talk about the ratio test. We'll do some exercises after this. So this is a pretty nice test. I will say after we have it, a lot of times students kind of tend to gravitate towards this one over all the others. There's nothing especially wrong with that, but don't leave the other ones behind if they're still useful. Certainly the nth term test for divergence is about the quickest test you can use, and the other tests are also pretty great if you can satisfy their conditions. So this is any series, and suppose that you take the limit as n goes to infinity of the n plus 1th term over the nth term, and you get some number rho. If rho is less than 1, the series converges absolutely. If rho is greater than 1, the series diverges. It's the ratio between the next term to the previous. If it's decreasing, so if it's less than 1, it's going to converge absolutely. If the ratio is increasing, the next term is actually bigger than this one, then it's going to diverge. And if it's equal 1, if they basically increase or decrease at the same rate, if they basically are equivalent, then it's inconclusive. Maybe it'll be small enough, maybe it won't be. That's the ratio test. Let's look at some exercises. The first one we're going to look at is problem number 5 from section 10.5 in our textbook. So let's see here. Ratio test then. The nice thing is that we are finding the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So with that in mind, I don't really have to consider the negative because it is an absolute value. So the nth plus 1th term, well, that would be n plus 1 to the 4th over 4 to the n plus 1. And then the nth term would be, well, what I have right there, n to the 4th over 4 to the n. So we're looking at the limit as n goes to infinity of this. Let's see here. This equals the limit as n goes to infinity of n plus 1 to the 4th over 4 to the n plus 1 times 4 to the n over n to the 4th. We cancel out the 4 to the n. This will be 1/4 times n plus 1 to the 4th over n to the 4th. And if you consider that, this part is just going to 1, because it's a rational expression with the same degree on top and bottom. Whereas, of course, this is staying to be 1/4, so this equals 1/4, which is less than 1, because that's our rho, which means converges absolutely by root test. Let's look at another one. Well, same idea. We have to look at the n plus 1th term, so the limit as n goes to infinity. N plus 1, well, n plus 1 minus 1 will be n factorial, so I'll go ahead and put it in, though. I might as well. N plus 1 minus 1 factorial over n plus 1 plus 1 squared over n minus 1 factorial times, or divided by n plus 1 squared. That's going to equal the limit as n goes to infinity. That'll be n factorial over n plus 2 squared times, flip that, n plus 1 squared over n minus 1 factorial so let's see, n factorial is n times n minus 1 factorial. So the n minus 1 factorial is going to go away. This is going to get us limit as n goes to infinity of n times n plus 1 squared over n plus 2 squared. This part is going towards 1. This is going to infinity. So this goes to infinity, which is greater than 1. Which is greater than anything. So, yeah, that's rho. So this would diverge. You might ask, does something diverge absolutely? Not really. There's no special divergence. We count it divergent if it just doesn't converge. So if it goes to infinity or negative infinity, as far as using the word diverge, it doesn't really matter. We usually do specify if it goes to an infinity. That's about as far as we go. Alright, let's talk about the root test. I'm not going to prove the ratio or root test. Their proofs are in the book. They are similar, so they're worth looking at. We aren't going to present them here. So the root test. We're also going to calculate this rho, but in this case the way you calculate rho is you take the nth root of the absolute value of a sub n. It's the same conditions on rho though. If it converges absolutely if rho is less than 1, diverges if rho is greater than 1, inconclusive if rho equals 1. Gotta use a different rule if that happens. Let's look at an example. So here we got convergence or divergence test, and we want to use the root test. So this is the nth root. Ln e squared plus 1 over n to the n plus 1. Well, that's the same thing as raising to the 1 over n power, so you can multiply their exponents. Ln of e squared plus 1 over n to the n plus 1 over n, which of course you can then bring down the exponent. That's n plus 1 over n times ln of e squared plus 1 over n. Limit as n goes to infinity. And I think you can see pretty well where this is going. This is going to 1. This is going to ln of e squared, which is 2. So that's our rho. And that is greater than 1. So we are going to diverge. I think the limits sometimes are a little bit more difficult to calculate using the root test, although not always. Some things, especially if they're raised to the nth power, are a little easier doing this. Let's do this one. This one's made much easier by the root test. So if we take the nth root of a sub n in absolute value, well, that's going to be the sine n 1 over square root n to the 1 over n. That's just going to cancel this out. So then you're just looking at sine of 1 over square root n. Limit as n goes to infinity. Which is just going to be 0, less than 1, converges. Absolutely. That's the end of our just ratio or root test problems. Let's look at some generic problems where we're just converge or diverge. Any test. This one is definitely flipping from positive to negative. So, show absolute convergence if possible, I believe is the instruction. No, it doesn't actually say that, but we will certainly check it. So let's see here. N factorial over negative n to the n. We have a couple options. We could try root test. If we do root test, it'd be the nth root of n factorial over negative n, well actually just n to the n, which would be the nth root of n factorial over n. The question would be what would happen with that, and that's something I don't necessarily know if I want to get into. I think honestly with factorials a lot of times you're better off using ratio test. N plus 1 factorial over n plus 1 to the n plus 1. And then divided by, so times, basically the flip of that, n to the n over n factorial. So this is going to be n times n plus 1 times n factorial, so that goes away. So we have n plus 1 times n to the n over n plus 1 to the n plus 1. I think I'll do something really fast since this is n plus 1 and this is n plus 1. Can reduce that. Yeah, so that becomes n to the n over n plus 1 to the n. Or n over n plus 1 to the n. I think this will go to 1. If we do our logarithm trick, our e to the ln of n over n plus 1 to the n, and then look at that exponent, I'm pretty sure that's going to go to 0. Yeah, because you'll get the n out front. So if you look at ln n plus 1, n over n plus 1 over 1 over n, that's going to 0 and that's going to 0 because ln of 1. You do the derivative, that's 1 over that, so n plus 1 over n times the derivative of the inside, so that is bottom n plus 1 times the derivative of the top minus the top n times the derivative of the bottom over the bottom squared over the derivative of the bottom, which is negative 1 over n. So that's going to be n plus 1 minus n will just be 1. N plus 1s will cancel out. So that gives us 1 over n times n plus 1 over negative 1 over n squared. Which would go to negative n squared over n times n plus 1. which would actually go to -1. So then this goes to e to the -1. Let's see if that's right. 1 over this times its derivative, so bottom times derivative of the top minus top times derivative of the bottom, with bottom squared. Plus 1 went away. Okay. Derivative of the bottom, that's n to the -1, so it'd be negative n to the -2, so -1 over n squared. So I'm just left with 1 there, nothing there, so 1, n times n plus 1. On the bottom I got -1 over n squared. Multiply up the n squared. That was unexpected, e to the -1. I really thought we'd get 1 because it's, you know, the inside's going to 1 and 1 to any power is 1, but apparently we're getting e to the -1. Well, if that's the case then, that is less than 1, so this should converge. Absolutely. Unexpected. Well, let's continue on. How about this one? I feel like we've done this kind of thing with tests before, but honestly, the bottom's increasing a lot faster than the top, so I'm pretty sure this is going to converge. But it's probably easiest to do ratio tests, so we'll go ahead and do it. N plus 2 times n plus 3, if you plug in n plus 1, over n plus 1 factorial, times n factorial, because I'm just dividing by this, over n plus 1, n plus 2. Well, first off, we have the nice case of these going away. This is n plus 1 times n factorial, so you can cancel out the n factorial. So this is going to be n plus 3 over n plus 1 squared. And of course we know that goes to 0. That is less than 1, so this converges absolutely. That wasn't too bad. Before we go on, I want to look at a special case. Just going to pencil in this problem. This will be exercise 29. We have the sum n equal 1 to infinity of 1 over n minus 1 over n squared. And if you look at this, if you try to do ratio test, you get 1 over n plus 1 minus 1 over n plus 1 squared divided by 1 over n minus 1 over n squared. So, I mean, you could get common denominators if you wanted. This would be n plus 1 minus 1 over n plus 1 squared over n minus 1 over n squared. So this would become n over n plus 1 squared times n squared over n minus 1. So we get n cubed over n minus 1 times n plus 1 squared. But that's just going to go to 1, which would be inconclusive. But honestly, this is a bit easier than that. You could think of it a couple ways. If you do get common denominators, you get a, let's see, n minus 1 over n squared. You could then do a comparison with let's see, make the top bigger. Yeah, n over n squared, which is a diverge. Well, that wouldn't help. That wouldn't help. I think I would just do this. This is a divergent p-series. This is convergent p-series. Sum of convergent and divergent series is divergent. Otherwise, I would just do a limit comparison test with this thing. I'd just do 1 over n, and then, do the division of the two. If you do n minus 1 over n squared over 1 over n, that's n minus 1 over n squared times n over 1, which would be n minus 1 over n, which would go to 1. Which for the limit comparison test means they have the same convergence or divergence, and since 1 over n is divergent, this has to be divergent as well. So there we go. The next set of problems we're going to look at have recursively defined terms. This is actually set up really well for the ratio test, because remember, ratio test talks about convergence using this. Well, you can actually solve for this in a lot of recursively defined sequences. Like for this one, I just divide both sides by a sub n. A sub n plus 1 over a sub n is now 1 plus inverse tangent of n over n. And then that will go to tangent of n as n goes to infinity will go to 1 plus pi over 2. Inverse tangent goes to pi over 2, and then of course this is going to infinity, so this is going to 0. That's less than 1, so converges absolutely. Alright then, we look at this one. If you set up the same work, a sub n plus 1 over a sub n is going to be n over n plus 1. Unfortunately, that goes to 1, which is inconclusive by the ratio test. Well, if we look at our result here, a sub 2 would be 2 over 3 times 3. A sub 3 would be 3 over 4 times 2 over 3 times 3. A sub 4 would be 4 over 5 times 3 over 4 times 2 over 3 times 3. So, keeping this in mind, this is 2 times 3 over 3. This is 2 times 3 over 4. This is 2 times 3 over 5. A sub 5. We'll just guess it's going to be 2 times 3 over 6. Let's see if that bears out. So this would be 5 over 4 times 4 over 5 times 3 over 4 times 2 over 3 times 3. 5 over 6, my bad. There we go. So yeah, 2 times 3 over 6. Well, with that in mind then, we can come up with just a formula for a sub n. A sub n is 2 times 3 over... It is 1 more than the index, so n plus 1. And since that's the case, that's 6 over n plus 1. That is, I can compare with, say, 1 over n. So 6 over n plus 1 over 1 over n. That is 6 over n plus 1 times n, so 6n over n plus 1. That goes to 6. They have the same convergence or divergence. And 1 over n is a divergent p-series, so divergent by limit comparison test. I'm jumping in here again at a later date because in reviewing the video for the edit, I realized I made a critical error. So here we got a series from the end of the section, which these are a little bit more difficult. You can see you've got a lot of n's here to deal with. We're going to try and do this one by the root test. I thought about doing the ratio test, but it just got really ugly when I put in n plus 1s in all the different places. Root test makes it a little simpler looking immediately, so I really think it's a bit better. Can really ignore this alternating series term. So if I just take the nth root of the whole thing, nth root of n factorial to the n over n to the n squared. Remember that this is the same thing as raising to the 1 over n power. So basically divide an n into both powers. You will get n factorial over n to the n. Now this is still not a super simple limit to evaluate, but we've done this kind of thing before. So if we look at this, equals limit as n goes to infinity of n times n minus 1 times n minus 2. Now note, as I'm doing this, we're not doing a test about a series at this point. This is just a limit of a function, a limit of a sequence. So whatever trick I can do to show that the sequence goes to something, I can do that trick. So I can actually do this and say, alright, this is bounded below by 0, and it's bounded above by 1 over n. Because 1 over n is this, and 2 over n is smaller than 1. 3 over n is smaller than 1. The only one that's not smaller than 1 is n over n. So multiplying by all of these just made 1 over n smaller. So this is less than just 1 over n. This goes to 0. This is non-negative, so this has to go to 0 as well. And then that's our answer. So rho is 0. That's greater than 1. Less than 1. So converges absolutely by root test. And there we have it. That'll be it for this section. Next time we'll look at the alternating series test. It's a test specifically for talking about the conditional convergence, the regular convergence of an alternating series. It isn't necessarily always the best test to use for an alternating series, but it works pretty well. So we'll look at that next time. Have a great day.